Aloha class, we are not on 4-1, so we're going to speed this bad boy up. We've been rolling in class. You guys have been doing awesome in class. Make sure you're coming in for help. All right, when you need it. We are on section 4.3, which is F prime and F double prime. So we're going to look at our graph of F, and we're not only going to just focus on increasing and decreasing max and mins, which would be those extrema values, but we're also going to now introduce a second derivative and how that relates to the graph of F, okay? In terms of the AP exam, we kind of do a couple of things here, okay? First would be topic 5.3, determining intervals on which a function is increasing or decreasing. We kind of have done that already. That helps us to find the extrema, which ones are mins, which ones are maxes. We have actually a first derivative and a second derivative test, which we're going to look at, which allows us to do things a little bit quicker. And then the main point of today will be determining concavity of functions over their domains. There's the enduring understanding, learning objective, and essential knowledge. But here we go. Let's go ahead and get rolling. There's a lot to do on your own right here, okay? And a lot of things that you should hit pause with and make sure you're okay with. All right, for example, the first one here would be a couple of these graphs we want to be very familiar with. It says, what does the value of each function's derivative tell you about the behavior of the graph? Well, let's go ahead. What is the derivative of f prime of x? Well, that would be e to the x, right, class? And g of x is equal to 1 over x. Now, the question is, what would those derivatives tell me about the behaviors of the functions? And what I want you to do is think about that very quickly and see if you can get an answer for that. Now, hopefully you said this, that for f prime of x being equal to e of x, that f of x is always greater than 0, right, class? And if it's always greater than 0, then that means the original graph will be increasing. F would be increasing over that entire domain. In terms of 1 over x, f prime of x, or g prime of x will also be greater than 0. Over the domain. And remember, it was a natural log. And remember, the domain of a natural log is from 0 to infinity. So that would mean g of x, the original one, would be increasing over the entire domain as well. So that's interesting to see about both of those. It says to sketch those functions. Hopefully we know e to the x, right? It's got that y-intercept right there. It has a horizontal asymptote. And look, it is increasing throughout the entire domain. In terms of, and we'll put a little f right there, in terms of g, do we remember that's an inverse? So if 0, 1 is on e to the x, then on the natural log would be 1, 0. And guess what? That guy is always increasing. So it's kind of interesting, right? You look at the derivative, you look at the graphs, they pan out beautifully. Now what's interesting is they ask us to find the second derivative, and do we notice anything? Second derivative, oh snap, it's just e to the x. Well, that guy's positive over the entire domain, isn't it, class? What about g double prime of x? Right? For that, we want to go back to our derivative up here. Shame on me. And that would be x to the negative 1. So that'd be negative x to the negative 2, which I could write as negative 1 over x squared. Oh, snap. That bad boy, g double prime of x, is always negative. Right? Now, what does the second derivative tell me about these graphs? Right? You kind of have that graph going like that. That'd be g. This would be f. Maybe it tells me a little something about what we call concavity. So let's keep on rolling up here. It says to make some note cards. Remember, class, you do not have to make note cards in this class. If you want to make note cards, go crazy. But we're going to go ahead and just have one little review problem here, okay, class? And then we're going to go ahead and introduce what this concavity is. It says, find where the function is increasing, decreasing, determine any local extrema. So remember, the way we want to do increasing and decreasing in AP Calc is we want to find critical points. And when the question asks increasing and decreasing, it should be light bulb, first derivative. So let's go ahead and find the first derivative, which would happen to be a product rule, which would be u times the derivative of v, which would be e to the x, plus e to the x times the derivative of u, which would be 2x. Okay? Now, remember, critical points are whenever the function is 0 or d and e. So I'm going to go ahead and set my derivative equal to 0. Now, when I set that equal to 0, I don't want to solve for x. That'd be silly. That'd be crazy. What I want to do instead is I want to factor, because factoring makes things a little bit easier. They both have an x. They both have an e to the x in it. And if I factor those guys out, I get an x. Ooh, shame on me. Plus 2 is equal to 0. Whoa, so we got a lot of things going on right here. Okay, we got x equals 0 would give me a 0. X equals, e to the x equals 0. That give me something, and then x plus 2 is equal to 0. Well, hopefully we know that boy right there is impossible. We got that from that initial one, and we got that. So we got a couple of critical points here for us. Okay, so let's go ahead and make a sign analysis for g prime of x. We put a -2 there. We put a 0 there. Remember, start getting really good at that mental math, okay? Let's pick a number to the left of -2, like -3. If I put a -3 in there, I get a negative. I get a positive, and I get a negative. A negative, a positive, and a negative would be a positive. All right, let's put a -1 in there, because a -1 is from -2 to 0. Put a -1 in there. Negative, positive, positive, that'd be a negative. And then let's pick a number bigger than that. Everything would be positive. We go right there. Right now I can answer all these awesome questions about that stuff. Right, class? So let's go ahead and answer them. Okay, g of x, let's have our conclusion. Okay, therefore, love the little therefore symbol. Therefore, g of x is increasing. Okay, because they asked me where is g of x increasing and decreasing. Is increasing from, let's say, what would that be? -infinity to -2 union 2 to infinity. And we always want to justify because g prime of x is greater than 0. You never want to say, hey, just AP greater, just check out that sweet sign analysis, right? We don't want to do that. So we want to make sure we always justify, okay? And we'll say, and g of x is decreasing, okay, on the interval from -2 to 0, and I probably should put on, increasing on, -2 to 0, because g prime of x is less than 0. Okay, so remember, after I do those two things, I could probably answer if we are dealing with some extrema, some local extrema. Well, that guy there, if it goes, remember I taught you in class, you know, we could do this kind of real ghetto here. Let's get away from that guy, we'll make it blue. It's going to increase, then it's going to decrease, and then it's going to increase. What would that be, class? That would be a relative or local max. What would 0 be? That would be a relative or local min. And I don't have enough room right here, but write a little statement that says that, right, class? We would say that at g of -2, right, that would be a relative max. Why? Because g prime goes from positive to negative. I don't have enough room, but write it down, okay? It's the important thing about getting to college is you got to be able to write down things that are important. When you write it in your own words, it kind of sticks in that brain a little bit better, okay? And then we would say g of 0, right? This guy would be a max, relative or local, and this would be a min. And why? Because g prime of x goes from negative to positive. Always, always justify in AP Calc. All right, let's roll from the warm-up. Concavity deals with how a graph is curved. A graph that is concave up looks like that, right? It's like a cup going up, right? While a graph that is concave down looks like this. It's like a cup that's going down, right? We can use the second derivative to determine the concavity of a function. Definite continuity, okay? Let y equals f of x be a differential, right? If it's not differentiable, you can't even figure anything out, right, class? The graph of f of x is concave up. If f prime is increasing, it's concave down. If f prime is decreasing. If the first derivative is increasing, then the second derivative must be positive. Okay, if the first derivative is decreasing, remember, these are rates, those are slopes, then the second derivative must be negative. Negative is that. Thus, instead of using the definition of continuity to determine whether the function is concave up or concave down, we can use a second derivative test for continuity. Concave up on an interval where the second derivative is positive, concave down where the second derivative is negative. Look at, I'm so happy. If f double prime is positive, it's concave up. If f double prime is negative, we are concave down, right? Positive, smiley face, concave up. Like when you guys get A's on your test. Oh, not an A, so sad. Okay, concave down. All right, let's keep rolling, class. I've been noticing when I use this, you guys like some face-ups. All right, example 2, using the same graph as our previous example, indicate which portions of the graph are concave up, which are concave down. Label the point where the graph changes concavity, what's going on. All right, so these are original graphs, so we could call these guys G, okay? Or right there, it's Y. I didn't know that was for the y-axis, and that's Y prime. So let's go ahead and take a look at this. If I'm looking at y, where is this concave up? Let's go ahead and make that red. Ooh, concave up. Let's actually just do it like we read a book. Go from left to right. Those are all cupping down. Right, class? Oh, that's a cup going down. So that would be concave down. So that means that guy's second derivative would be positive. Shame on me. It's concave down, so the second derivative would be negative. Vice versa. Check this out. It looks like right around here it changes concavity, right? It goes from down to up. So the red would be concave down, the second derivative negative. The blue would be concave up, second derivative being positive. Very interesting. Now let's change our thought process a little bit, which kind of messes us up a little bit. What if I'm looking at the derivative graph? It says, label the x value where the graph changes concavity. Verify this with the definition of concavity as it relates to the first derivative. Okay, so when we look above, that kind of looked like it changed, right, class? From concave down to concave up. Vice versa, let's take a look at this, right, class? That is the first derivative graph, right? We just got done doing this in chapter 3. That's the first derivative graph, and you notice it's all decreasing, right, class? And then if we look after it, okay, this is always increasing. And if we go back to that chapter 3 that we did when we looked at these graphs, okay, right, where we had horizontal tangents would be up there and about right there, right? We have horizontal tangents, those guys would cross, right? And then it was kind of when you were increasing and then decreasing, that's where it would be above or below. But now let's look at just the first derivative, right? Those are always decreasing. If you remember, that entire red was the entire red for up here, right, class? Ooh, I think I'll do a better job if I'm over here kind of putting my face right in between this, right, class? Okay, let me go back. Ooh, snap. Okay, but if you compare that, I want you guys to compare that graph to the graph that was up there. Okay, and if I'm comparing those graphs, the reds match up beautifully. Do you see that? The blues match up beautifully. So what we kind of want to introduce and what I want you guys to write down right here, is the following. Ooh, you guys almost saw some tests going on right there, right? Okay, is that on the interval, okay, if you notice from 0 to -3, okay, from 0 to -3, f prime is decreasing, okay? F prime is decreasing. And since f prime is decreasing, we say that f is concave down. Remember, we're always using information to tell us information about the original graph, okay? And then if we focus on the interval, ooh, you know what? Let's color code this bad boy. If we focus on the interval from -3 to, let's say, infinity, okay, f prime is increasing. And if f prime is increasing, what does that tell me? That tells me that f, the original graph, is concave up. Okay? Now, if you notice, they say, hey, sketch the graph of f double prime on the same grid. So I'm going to make that black, okay, you guys? Remember, the way we do those derivatives, you know what? Hit pause right now. Try it on your own. Okay? But we use the horizontal tangent. That means it's going to be there. Those guys are all negative, so it's below. That goes out positive. That's above. Ooh, notice that the concavity of f changes when the second derivative changes signs. Okay, so it's got to change signs. It's got to go from positive to negative or negative to positive. In this case, it changes from negative to positive. So it's kind of cool how it matches up. Take a real quick look at this, right, class? I'll make it this cool little yellow. Okay, there we go, right? That changes concavity. Ooh, look where it was on the first derivative. Ooh, look where it was on the original. Okay, that is very important that you understand the difference between those three graphs and how we use the first derivative or the second derivative to help me tell about concavity on the original graph. Okay, here, let's focus on what you guys will have to do for the AP exam. All right, this right here asks me to focus on that and tell me about concavity. When is it concave up? When is it concave down? Well, right when you see that, you should say, oh, light bulb, second derivative. But in order to find the second derivative, we have to find the first derivative. Okay, now I want you to go, as you're going through this, right, if I asked about increasing, decreasing, max or mins, I would use that first derivative and do a sign analysis, and that would answer all those questions for us. But this one specifically says just to focus on concavity. So guess what? We're just going to focus on the second derivative in the second derivative test. Okay, and so I'm going to find that guy. What would that be? 12x squared minus 24x. Okay, so just like, the beauty of math is it kind of just, it has steps. You just keep on going up some steps, and they kind of build upon each other. So we're going to do the same thing we did before. For the first derivative, increasing, decreasing, we would find critical points, and we would do sign analysis. So we do the same thing for the second derivative, okay? Let's go ahead and find critical points. Well, how do I find the CPs? We set our second derivative this time equal to 0. Let's do a little factoring. Okay, and I get a critical point of 0 and 2. So come over here, do a sign analysis for 0 and for 2. All right, let's go ahead. A number to the left of 0, -1. Put a negative in there. I get a negative. Put a -1 in there. I get a negative. That's a positive. Let's put a 1 in there, a positive, a 1 in there, a negative, negative. Put a bigger positive, positive. Booyah. Look at how sweet that is. I can just answer all my questions now. So let's do it. Oh, I might have ran out of space. Let's do it. Let's do it over here. And I will do it in a different color so you guys are all okay. Therefore, okay, g of x is concave up on what intervals? It's concave up from -infinity to 0, union 2 to infinity. Because the second derivative is greater than 0. I'm not even going to write the next one. You hit pause and you write it down. Okay, hopefully you wrote it down, and it should say g of x is concave down on the interval from 0 to 2. Why? Because g double prime of x is less than 0. Okay, so hopefully you hit that pause, and hopefully you're challenging yourself to do those on your own. You're going to learn a lot. Now we have this. Now if you look down here, okay, we have something called a point of inflection. A point of inflection is where the graph of the function has a tangent line. Even if it's a vertical tangent line, and where the concavity changes is called the point of inflection. So the question is 0 and are 2 points of inflections, P of i's. And guess what? They are, why? Because g double prime of x changes signs, right? We don't care if it goes from positive to negative or negative to positive. As long as it changes signs, the second derivative changes signs, we say that they're points of inflections. Since, okay, we're supposed to example 5, just says, where do you think a point of inflection would occur? And remember, it changes from concave up to concave down. So if I'm just following this little curve right here, right, that looks like it's concave up, concave up, oh snap. Looks like right there I changed from concave up to concave down. Oh snap, right there. So it's each time, so that's concave up, concave down, concave up. So those look like they would be points of inflections. Okay, what about this? Ooh, that's concave up, concave up, concave up, concave up. Oh, snap. Looks like right there it changes, and now I'm going down. Going from cupping up to cupping down, right? And then this guy right here, let's go. Concave up, concave up, concave up, concave up. Didn't look like I changed anything, so it doesn't look like there's anything there. Since points of inflection occur when the graph changes concavity, and a graph changes concavity when the second derivative changes from positive to negative or negative to positive, we now have an easy way to determine points of inflections. Okay, let's keep rolling, y'all. Okay, second derivative related to points of inflection. It's just what we just said. If it changes from positive to negative or negative to positive, then we say it is a point of inflection. It's going to make a lot more sense if we just start rolling. One of the biggest mistakes made in AP Calc is this important thing right there. Just because the second derivative is 0 or DNE, which means it gives me a critical point, it does not guarantee that it's a point of inflection. You want to remember, it's only a point of inflection. It changes from pos to negative or negative to positive. What the heck am I talking about? Well, let's do the next example and check it out. Find the points of inflection. Points of inflection, concave up, concave down, all wing, ding, ding, second derivative, right? So let's go ahead and find the second derivative. In order to find the second derivative, we have to find the first derivative. 15x to the 4th plus 40x cubed plus 15, right? If I wanted to find increasing, decreasing, max, mins, I would use that. But I'm going to go here and go 60x to the 3rd plus 120x squared. That is going to tell me points of inflection, concave up, concave down. In order to do that, I want to know when the derivative is 0. And please, we always forget We always want to find when the second derivative is DNE. But since I have no radicals, no denominators, the DNE gives me nothing in this problem. So let's go ahead and find out when this guy is equal to 0, which would be, I would factor out. I'm kind of skipping a couple steps. I apologize. 6 is that's g double prime of x. Let's factor 60x squared. And then if I factor that out, I get an x plus a 2. So I get a couple critical points at 0 and at -2. So then I'm going to do a little sign analysis. And I just need to know, right, if it's a point of inflection, if the second derivative changes signs. So the sign analysis is awesome for this. Let's plug in a -3 and -3. Oh, that'd be a positive, and -3 would be a negative. So I get a negative right there. -1. -1 would be a positive, and -1 would be a positive. So we go booyah. And then let's pick a number bigger than 0, like 1 million trillion billion. Positive and positive gives me a positive. Oh, snap. 0 is a critical point. But is 0 a point of inflection? No way. Jose. Okay, so believe it or not, at g of -2, therefore, g of -2 is a point of inflection, right? Because the second derivative changes signs, right? And then what a lot of students make the mistake of, they just assume because it's a critical point for the second derivative, it has to be a point of inflection. But no, it's got to change from negative to positive or positive to negative. And that dude at 0 went from pos, which means it's not a point of inflection. Could you draw what a graph like that look like? If you can, you are on top of it. Okay, class, now what we're going to do is I'm going to show you a relationship between the first and the second derivative. And we have this special second derivative test to tell me whether I have a max or min. It's just like another way, right? We usually do sign analysis using the first derivative, and that can tell me whether I have a max or min. But we kind of have this cool little other way to tell us if we have a max or min also, okay? And for us to understand this, what we're going to do is we're going to look at an original graph of y. And if you look right there, right, class, that's definitely a max. Okay, when you look at that max right there, is it concave up or concave down? Right, that's a max, and if the relationship I want you to see is that's concave down. Okay, it's concave down right there. Okay, vice versa, I want you to look right there. Right, class, that would happen to be a min. Now, what do you notice about that? At that min, it's concave up. And that's not just by luck. That is always going to happen. When you have a max, it's going to be concave down. When you have a min, it's going to be concave up. So when we do a first derivative, and we find out that, hey, that first derivative could be a critical point, which gives me a max or min. If I check the second derivative, that can actually help me out. Okay, because second derivative, right, tells me a little bit about concavity. So I'm going to show you how we use that here, okay? So here it is in a nutshell, and then we will do an example. Second derivative test. If f prime of c is equal to 0, okay, and thus a critical point, and the second derivative is less than 0, we know it's a max, just like I showed you above. Right? If f prime of c is equal to 0, thus being a critical point, and it's a big one, and the second derivative is greater than 0, it's going to be a local minimum. Okay? Let's go ahead and do an example so you guys can know exactly what I'm talking about. It says to example 7. And some people don't like it when I show you a different way of doing things, but it's kind of cool sometimes to have multiple ways to get the same job done. Okay, so here we go. Let's go ahead and find. First, we want to find, right, because we're trying to find mins and maxes, but we're going to use the second derivative to help us out. Okay, so I'm going to go ahead and find the first derivative here, and I'm going to show you how we use that, okay? So we get -4x cubed, and this video is running a little bit long, so I'm going to use some of my notes to make this math super duper easy, okay? So here we go. We're going to factor this because we want to find critical points, right? Everything has a -4x in it. If I take a -4x, I get a little x squared minus 3x plus 2. I want to set it equal so I can find critical points. I'll factor it really quickly for you guys. That's what x minus 2, x minus 1 equals 0. So I get critical points of 0, 1, and 2. That's a lot. So you could come over here and do a little sign analysis to help you with some max and mins, okay? But the whole point of this lesson is we are going to do the second derivative to help us out instead, okay? So just buy into having a couple, and I'm going to make it blue. 2 ways to do the same thing. All right, so here we go, g prime of x, okay, and g double prime. And we'll always go back to this guy because we wouldn't want to do the product rule or anything crazy like that. And if I find that guy's derivative, that would be -12 x squared plus 24x minus 8, right, class? Look at my sweet little notes here. Oh, I'm not even going to do that. What I am going to do is use that little notes that I had up there using the second derivative test, and I'm going to do g double prime of 0, g double prime of 1, and g double prime of 2. Now, what I need you to do right now, so that this totally makes sense, go back up there really quickly, look at the notes. And since these are critical points, 0, 1, and 2, if I plug them into the second derivative and they give me a result, what would that tell me? Okay, hit pause, go ahead and do that math. Actually, I'll give you the answers right now, right? If you go g double prime of 0, I get an answer of negative 8. G double prime of 1, and I plug that 1 in there, I get an answer of 4. And G double prime of 2, I get an answer of negative 8. What do those results tell me? Hit that pause button, go up there and see if you can figure it out, okay? For the first one, okay, for these two negative ones, okay, I had a critical point, but the answer was negative. What the heck would that mean? That would mean it's concave down. If it's concave down and that was a critical point, right, I think it's always helpful to draw that. That means at 0, therefore, let's go therefore. Therefore, at g of 0 and at g of 2, right, class, I get a relative max because g prime of 0 and g prime of 2 were CPs and g double prime of 0 and g double prime of 2 were less than 0, right? Exactly what that thing said above. And then obviously this guy's different, right? That would be a critical point. Whoops. That would be a critical point. It'd be concave up. If it was concave up and it was a critical point, that would have to be a minimum. You write that statement. This thing went 20 seconds. I'm trying to keep all these under 25 minutes. Aloha.